lecture.
Recording in progress.
And we discussed the case of states being equally likely. So this would correspond to the case we started discussing Tuesday. We just reviewed again on the board of throwing dice, where every phase has an equal probability. Now, in reality, that's of course not the case, right? Because your die would have to have perfect shape, atomically perfect shape, which never happens. Also, the way you throw it must be completely random. But you can imagine a die that is biased to one phase or another. And then you can ask what would happen with this distribution. Right? And the peak would definitely shift towards that value of the sum of the phase values towards which the bias happened, right? Now, similarly with energy states, if you have two energy states to populate and one gets a higher probability than the other, one has a higher energy than the other, the Boltzmann probability tells you how the probability was shifted, right? So now we are no longer just summing up the values, but in front of each value, there's a probability. Right? And that's the only difference, right? So in the case of the dice, you have equal probability. So you can pull the probability in front of your averaging sum. In the case of different energies, you then have attached a different probability in front of each value. Right? And so you can see immediately how that impacts your averages. With this, I'd like to now go to the next subsection, and I believe it's the letter D, where we would like to explore the link to the partition function. We have arrived at a general expression for S as the Boltzmann constant times your capital A logarithm A minus the sum over our states logarithm AI. And we have encountered these population numbers already when introducing the Boltzmann factor, right? So remember, your Boltzmann probability is AI over A, and hence our population number is nothing else than probability times A. So if we make use of this for this part of the expression, it simply comes the sum over A BI logarithm A BI. Now, I can pull the A in front of this, since it's independent of the state. And I can also apply the logarithm rules where I have two terms now. Okay. Now, this logarithm here is also independent of the sum. So I can pull it in front of the summation. And I obtain this expression. And I can see that this is the sum over the probabilities, which must be 1. Okay. So I have a sum bi logarithm bi plus a logarithm a. Now, if I come back to our S above and I insert what I've just obtained for this term here, then you see that I have an a logarithm a and an a logarithm a, but there's a minus in front of it. So these two annihilate each other, and I'm left with minus kb a sum over pi logarithm pi. I can, so I like this expression very much. If I divide by capital A, I find that my S of the system is minus KB sum over pi logarithm pi. And this is the same as saying my S of the system is minus KB expectation value of logarithm p. This is one of my favorite expressions for the entropy. I find it very intuitive. It tells you that the entropy will go up if your number of states goes up, right? You're collecting more terms. And it goes up if your probability goes up, which means your energies go down. So the more states you have with low energy, the more entropy there will be in your system. So this is the explanation why you would always argue a molecule with many conformations will have much more internal entropy than a rigid molecule, right? Because all the conformational angles give you many minima states with very similar energies, right? While in a rigid compound, you don't have that many states. Now, I can also continue with the expression up here and now write more explicitly my my entropy, so let's also here divide by A, right, of the system as minus KB sum over probabilities. And now I insert my Boltzmann probability values. So the e to the minus beta ej over q. Okay. Now that is by virtue of the logarithm rules, logarithm e to the minus beta ej minus logarithm of q. And this is simply minus beta ej. So this gives me KB beta sum over pi. Oh, and I'm truly sorry, I messed up big time here. To be consistent, this is of course the energy I. So I'm using I now for my state, right, with the probability I. EI plus KB sum pi logarithm q. Again, this logarithm here can be independent of the state, so I can pull it in front of the summation symbol, and then this one becomes equals 1 again. So also, if I look at the first term, you might recognize the expression we have used for the internal energy U. Right? And your beta is, of course, 1 over kBt. And so the constant will cancel. And what you have here is 1 over T plus KB logarithm Q. This is another very common expression for the energy, for the entropy. And also easy to memorize. Now, if you recall, our internal energy was also kBt squared derivative of dt logarithm q. So we can again rewrite this as kb. The t squared cancels with the t, so only one t is left, and then dt logarithm q for the first term plus kb logarithm q. So all these boxed equations are very common variants of the entropy expressed within statistical mechanics. Are there any questions in this reformulation? Or it's literally just inserting the definitions we've obtained previously. Yes, please.
This is the equation of the entropy in terms of the internal energy and heat, right? It's entropy in terms of internal energy.
So we come to this now. What's the link to heat? But no, so Q is not the heat. Q is the partition function. Yeah, I'm sorry. So you have, indeed, this the internal energy is U, but the second part is the logarithm of your partition function, right? Just to remember, this is simply the sum over the Boltzmann factors. Okay, I'd like to now look at the link, and this would be subchapter E, the link to heat. And I do have apologized for the use of symbols. It's the entire field. For some weird reasons, they decided to call Q the partition function and Q the heat. So we are using the same, literally the same letter. Now, we have the capital Q for the partition function of the entire system and the small case letter Q for the heat. But beware, this nice distinction will not hold, because for the partition function of an individual molecule, the field has selected the small case letter Q, which is literally identical to the small case letter Q for heat. Don't ask me why. There's a lot about conventions in academia. I don't know if you noticed. And a lot of our job is to tell you what are the conventions so you understand what people are referring to. All right, so what's the link to heat? We want to vary du because that's the change in work and the change in Q. And we had already, again, right, heat. We had already noticed that our change in heat is the sum over our states and the change in, so the sum over the states with the product of energy, the eigenvalue energy, and the change in the probability. And that we identified as CVDT, C above, okay? Just to remind you. Now, let's use my favorite expression for the entropy. And now let's also use, so let's consider this. And then we also would like to consider that change in entropy. And now if we write this total differential, right, we just above have seen there's a sum of states over states. So we have to sum here also over these states. And now for every state, we need to differentiate with respect to the probability. And then we have the variance in the probability. Okay. So this is just the total differential in all those states. Now, what is this derivative? We can simply look at this above equation, which will tell us that this must be, right? If I differentiate my ds with respect to dp, I have minus kb. And now I differentiate the sum over states I with respect to one of the terms. So all other terms die. I'm left with dpi of pi logarithm pi, right? So now I'm supposed to differentiate this product of these two terms. Let's do that, minus kb. So I differentiate p logarithm p with respect to p, and then I have let's make this really explicit. All right, this is the product rule. This means I get logarithm of pi here, since differentiating p with respect to p gives me 1. And then I have to multiply pi with the derivative of the logarithm p with respect to p, which gives me 1 over pi. So these guys cancel. And I'm left with minus kb logarithm pi plus 1. So this I have to insert back in my total differential. And my minus kb is pulled in front of my sum. Okay. And now I can factor out, or factor in my dp. Okay. And the sum over my changes in probabilities, right? If I change every probability by something, I will get a new probability. Okay. And the sum over the new probability must be 1, right? Which means that the sum over all my changes in probabilities must be 0. So this then means what I'm left with is this kb, my sum or my logarithms. And now let's insert back again our Boltzmann factor over q times the change in the probability, right? Now again, I can use my logarithm rules. So I have minus beta ej here, logarithm of the exponential, gives me just the exponent. Minus logarithm q. Excuse me, I forgot the dpi. Sorry, this is ei minus logarithm q dpi. And again, I have to sum. Okay. What we see here on the right, in the right-hand term, is the logarithm q, but that's independent of the state again. So I can pull it in front. So this expression here is logarithm q sum over I dpi again, this must be 0. Okay. So that's very convenient. And so what we are left with, the two minuses cancel, and we have KB, the beta is in front, sum over states energies dpi. Fine. And again, all of these equalities hold, and this is our ds, right? And we before highlighted and reminded you about our change in heat to be the sum over the energies with the variations in probability. And sure enough, you see it here on the right-hand side. This is our dq. Now again, what is beta? 1 over kbt. The constants cancel, and we find that ds must be dq over t, which is exactly the result you would expect from classical thermodynamics, if you remember. Now dq is also cv dt, and hence our delta S can be obtained as the integral over some temperature change of Cv over T. But also that expression you should have seen already. But you can now see that this is completely consistent with what classical thermodynamics gives you. And we have arrived at these useful expressions without a single experiment. Are there any questions on this derivation? Is there a math step that's not clear? The level of math, I hope, is acceptable to you. It should be. And so it's not necessarily complicated math. It's just that the symbols are maybe new, and we use it in multiple steps. And but other than that, it should be quite straightforward. Okay, let's discuss the example of, and similar to the energy we had before, the internal energy, of the monoatomic ideal gas. And always worth to reiterate, the ideal gas is quite realistic for any rare gases, right? So it's not an esoteric example unrelated to reality. Now, of course, more complex gases or molecules should then be dealt with more carefully. But in this, for such gases, we already discussed the partition function of the entire system can be written of the partition functions of the individual atoms, with n being the number of atoms. And this is the ideal partition function then that tells us 2 pi m over Planck's constant squared beta raised to the 3/2 times volume and to the power of n. So what you have in here is the small q, and this is the small q, the partition function of an individual atom regarding its translational motion. We will derive this partition function later on in this course. Right now it's just a given, but please, this is not heat, okay? Be careful. So we always have to ask ourselves when seeing such symbols, is there a dual meaning to them? And if yes, what could be the specific meaning in this context? Now, let's use this expression for the entropy. Hang on, I just want to verify my notes. Yeah. KBT dt logarithm Q. And we also had U over T plus KB logarithm Q. Now we know already the expression for the internal energy was 3/2 kB nt, and now we have to derive this, divide this by T, so we have kB, 3/2 kBn. Plus kB logarithm Q. And now we insert our expression with the little q, 3/2 kBn plus kBn logarithm small q minus kB logarithm n factorial, right? That's this equation here we've been using. And for this term out here, we can use again Stirling's formula. Excuse me, kBn logarithm n plus kBn. This is Stirling. Okay. So I'm noticing we are hitting the hour. Let's maybe not rush things now. I would like to ask, are there any questions right now? If not, we hold everything and we continue on Tuesday. I hope you will survive the incredible tension that has built up and that you can enjoy your weekend nevertheless. Thank you for your attention.